Not this great source, but was this because of some sort of either injuries or
Where's my snipping tool? I'll just write on the board. No, well, no, I was looking for, like, my print screen button is not working. Oh, there, now it is. And so I was looking for the snipping tool icon, which I keep on the taskbar, and it was not on the taskbar. And then lately, this computer has been not pasting, just deciding not to, but. All right. Yeah, but it did this time. All right, so everybody, are we all ready? Okay, so we're supposed to fully reduce the number of states and construct the reduced state table, make it clear which states have been combined. Now notice our output, we have 4 different outputs. So our first partition is going to be everything all together, all at once. A, B, C, D, E, F, thank you. H is going to be P0. And then P1, we're going to break it up based on output. Now there's 4 possible different outputs: 0, 1, 1, 0, 1, 1, and 0, 0. We don't have any 0, 0s, so we'll put we'll just have 3 partitions here. We'll put everything that has output 0, 1 together. So that would be A, B, D, F, G. Everything that has 1, 0 together would be C and H. And everything that has 1, 1 would just be E. At this point, I always check to make sure that I have everything, and I only put anything in one category. A, B, C, D, E, F, G, H, yes. Okay, so now, any questions on that first step? Okay, so now I'm going to look at where they go for W equals 0. So I'm just going to draw underneath here. So A goes to E, B goes to E, D goes to E, F goes to H, and G goes to C. Now I'm just going to label these little groups up here. I'm just going to call them 0, 1, and 2. So E is group 2, so these all are going to group 2. The H is going to group 1, and the C is also going to group 1. Okay, so so I can then split this one into 2 groups, into A, B, D,
That'd be P2, no?
and F and G, yes. Now let's see where C goes. C goes to H, which is group 1. H goes to C, which is also group 1. So they can stay together because they're going to the same group. You don't have to check the singlets, the things that are by themselves, because they can't split up. So that was checking the 0 followers. Now I'll check the 1 follower. So now I want to see, where do they go when W equals 1? So when W equals 1, A goes to F, B goes to G, D goes to F. Okay, so F and G are in the same group. They're both grouped together. And so these are all going to the same group, so I can leave them together. F goes to F, and G goes to G, which are in the same group, so they can stay together. H goes to A, and C goes to B. Turns out A and B are in the same group, so they can stay together. And E, we don't have to check that. So, did we make any changes on that last partition?
No.
So, and if we didn't make any changes, then we're not going to have, and we only have one input, we're not going to have another change if we go back and check 0 again, because we didn't make any changes with the 1. So we now know that we have divided this up correctly. Did you have a question?
Yeah, why don't we have to check E?
Because I can't split E up.
Oh,
So, yeah, yeah.
If we did have another change,
Yeah.
would we check in order to like see if there's any more changes?
So we just checked 1. We would go and check 0.
Yep.
And then if we didn't have any changes, we'd be done. If we had changes, we'd check 1 again.
Okay, so sometimes people will check 0 and 1 at the same time. Is that
Yeah.
not a good thing to do?
Yeah, you know, you can do that.
But whenever you have another change after that, then you have to do it one by one? Or,
You can always do it together if you're careful.
okay.
You are able to, there is just an answer, and if you can see it, you can just see it. I find I do better usually being methodical. Every once in a while, the pattern is so clear that, these guys are all going to be in the same group that I do that. But, yeah. I think it's best. Teaching it, presenting it, I'm going to do it one at a time. Okay, so then my table, my reduced state table, will have present state, next state, W equals 0, W equals 1, and output and my states, I just pick one representative. I always pick the lowest one alphabetically, but there's not a rule on that. So then A goes to E, and that is a letter I can use. And when W is 1, it goes to F, and I can use that one. And our output is 0, 1. F goes to H, which we're calling C. And then F goes to F, which we're calling F. And the output for F is 0, 1. And then C goes to H, which we are calling C. And C goes to B, which we are calling A. And then the output for C is 1, 0. And then E goes to E. And then E goes to D, which we are calling A. And the output for E is 1, 1. So that is our reduced state table.
There was a mistake in like not splitting it up enough. Would it be obvious based on your chart, your final chart? No. Okay.
No, because I do these wrong all the time, and I never notice. Yeah. Other questions?
Did anybody do that for the elevator project?
What?
State minimization?
I did last semester.
How long did it take?
Well, I didn't do it like this. I did it more holistically. Kind of like I knew certain states would act the same. Okay, let's take a look at some of these true-false quickly. Actually, let's take a look at the ones that I called yes, no. Where are they? Okay. Is a sequential circuit required? So what do I mean by a sequential circuit? Hmm?
So like, if we have memory,
It has memory, and we use flip-flops for those. Okay, so, question 1. An output signal must go to 1 only after an input line A remains high for 3 consecutive clock cycles. Are you required to have a sequential circuit for that, or could you do that with combinational?
it is required.
Yes, it is required. Okay, an output Z should be 1 if and only if 2 control inputs P and Q are both high at the same time. Nope, you can certainly do that one combinationally. A light must blink once each time a button is pressed, regardless of how long the button is held down.
So no.
Because, well, 5 seconds.
I would think that would be a yes. I would think that would be a yes. Let me check. I have my answers somewhere.
Yes, it was no.
I guess because it's, yeah, like it needs,
Because it needs to know it's because it's only blinking once.
right, it's not like, right, because you're saying regardless of how long the button is held up. Yeah, that makes sense. It just needs to blink. So, yes.
I put the answers here.
No, don't worry. Right.
Where did I put the answers? They are in my LaTeX document.
Yes.
No, why would you need a sequential circuit for oh, if it's own, that would be positive edge trigger. Does that require what?
Here we go. Okay. We said 3 yes. So 3 was yes. Okay. Now
Or negative edge.
what about number 4? A controller must detect the exact sequence 1101 on an input stream and then raise a flag. Yes. A temperature monitor turns on a fan if the current temperature sensor reading is above a threshold and off otherwise.
I would say no.
I would say no.
I would say no.
It's only the present
Because it's
state
just a-
cares about.
Yeah, I would say no.
Oh, I see.
If X is greater than Y.
And I
It's
have
a,
Yeah, basically.
no. The fan on-off decision depends only on the current sensor reading compared to a threshold, which is a purely combinational comparison.
What does it say about lightness move 3?
That one was a yes.
That was a yes. We must remember the button was pressed and generate only one blink until the next press. Okay, so now let's look at some true-false. In a synchronous sequential circuit, the output can depend both on current inputs and the history stored in the flip-flops. Synchronous means it happens on clock cycles. Yeah, yeah, yeah. A Moore machine bases its outputs solely on the present state, not the external inputs.
Isn't that one true?
That one's true.
Wait, really?
Yeah,
that one's true.
that's the definition of a Moore machine.
Is there true false questions on the exam?
There have been in the past.
Good thing you get to take the package as notes.
So yeah, you can bring anything.
That's true.
Yeah, you can bring anything. This is. Mealy machines can respond to input changes in the middle of a clock cycle, potentially producing faster output changes.
And it's running your classes.
In the middle. Well, I guess that is true, actually, yeah.
We have done that before. Let's see if that's what we're supposed to be able to do.
No, that does make sense, cause it's like, that's how it's synchronous.
Yeah.
You have to,
Yeah, 'cause
It's just the wording there.
The wording is weird, but let's see. True, yep,
Yeah.
yep,
That makes sense.
that makes sense,
Yeah, we talked about
because I certainly have programmed them that way.
Yeah.
And do you know why we missed the
He's got other things to worry about.
Every synchronous sequential circuit can be modeled by some finite state machine, but not every asynchronous circuit can be so modeled. Ooh, yeah, that's a good question. I don't know if y'all talked about that.
I mean, I would say true, but
I'm gonna go with false.
I think that is true, but let's find
Only on
out.
the basis that the last three have been true.
That is
that does
true.
make sense.
Synchronous sequential circuits naturally correspond to finite state machines, but some asynchronous circuits may exhibit complex or unstable behavior beyond standard finite state machine assumptions.
so it's basically saying every synchronous can be modeled, but finite state machines cannot necessarily model asynchronous.
That's right, that's what it's saying, yeah.
Wait, so I'm sorry, number 3 is true because you can have a negative edge trigger?
Number 3 is true because the output depends on the input, which does not depend on the clock cycle.
Oh,
Oh,
so,
in the beginning, I see.
So with the Mealy machine, you can have the output happen just like you do this, like, think of the basis board, just you do the switch, and that can make the output change, but that's not necessarily the clock cycle.
okay, that makes sense. I was just always thinking that stuff had to happen at a positive or negative edge of the clock.
The state changed.
The main goal of state minimization is to reduce hardware complexity without changing the recognized language or behavior. Oh, I think it's
I
true.
think that's true.
I think it's true.
So it's like less states means less.
Yeah,
Needed.
to reduce hardware complexity without changing the, yes, so that's true. All right. A single JK flip-flop can store exactly 1 bit of information, making it useful as a state memory element.
It can store.
Two?
I think it's just one.
Just one. All flip-flops store 1 bit of information.
That's true.
So that is true. Unlike synchronous circuits, asynchronous sequential circuits rely on the propagation delays of the gates to define their behavior instead of, y'all never did that, so you can skip that. Yeah, we can skip that.
I'm gonna say false.
What is it?
It is true.
Of course.
These have all been true so far.
Yeah, so.
Oh, have they all been?
Yeah.
If I was.
I see a false one.
There has to be one false.
There are 2 false ones.
If I was in a casino, I'd definitely
Okay.
bet on true.
A state diagram and a state transition table for a given finite machine represent the same information in 2 different formats.
So
What's a state transition? Like, what's the difference
Is it
between
a
that?
transition? Is this a state?
It's a state table.
Oh, I see. Yeah, I mean, it's
That's true.
Dude, I would've doubled it.
Yeah.
Removing memory elements, flip-flops, or latches from a sequential circuit can reduce it to a purely combinational circuit.
True.
Yeah. It's the flip-flops that make it sequential.
Right.
In a typical synchronous system, the outputs only change immediately after the active clock edge. Notice that doesn't say positive or negative, it just says active, whichever one you say is active.
True.
That one is true. That's typically how it's done.
Okay, so the last 2 are false.
Wait, no, there's 18.
No, there's
more,
another
there's
page.
more.
Oh, there's another page? Okay.
Yeah.
A one-hot state assignment means only a single flip-flop is ever set to 1 for any valid machine state.
Oh wait, the 1 hot means the 0 is true, right? No, it
No.
means that you have 1 0 0 0 1 to make it 1 true, right?
One hot means that only one single flip-flop is ever set to 1 for any valid machine state. It means that of your outputs, They would all be 0 except for one of them. So like your states are 0001, 0010, 01001000.
I guess.
Those are your states. So one hot encoding means that your states, each of your states just has one 1 in it. So how many flip-flops do you need if you have, just in general, if I don't give you any restrictions, how many flip-flops do you need if you have 5 states? 3.
It's less.
Because 2 to the third is 8. How many flip-flops do you need if I say you have to use one hot encoding and you have 5 states?
5.
5. Because you can only one of them can be 1 at a time. So it's your states would be 0000001, 00010, 00100, and so forth.
So the anode display is one hot. What is it? It's not one.
No, it's active low.
Active low, but it's same thing.
So it's one. It's
Zero
one low. Active. It's one
One cool.
cool. In a Mealy machine, the output logic depends on both the current state and the current input.
False. Wait, true.
True. True. If 2 finite state machines recognize the same language, they must have the same number of states.
False?
That's false.
That doesn't even make sense.
Yeah, I'm not sure when it says recognize.
Well, I mean, like, if they both use Verilog.
I see.
Yeah.
Okay.
To detect a particular input sequence, you must build a combinational sequence circuit only with no feedback or flip-flops. That's false. Yeah.
Because it needs to.
A sequence detector is definitely a sequential machine.
Right, exactly.
The setup time of a flip-flop must be met to ensure reliable operation in a synchronous sequential circuit. That's true. You have to pay attention to the setup time because if you are going too fast, then you don't have time to register the states. We've seen that some when we're using a test bench. A finite state machine described by n flip-flops can have up to 2 to the n reachable states, but some may remain unused. That is true. The output of a Moore machine can change immediately when the input changes, ignoring the clock.
False.
That is false. State encoding directly affects the complexity of the next state logic in a finite state machine design. And what does that mean?
State encoding, what is that?
What does that mean?
I don't know.
Okay, so how you define the states? Do you define them as like you have A, B, C? Do I make that 000111, or do I make it 011110? I mean, does that affect the complexity of the next state logic?
Yeah, you can make it more complex. But
Yeah, I guess we could.
Well, let's say that we have 3 states, and we just use 3 2-bit numbers. How we assign them, does that make a difference to how complex the logic is?
No, it could confuse you though, I guess.
It actually can.
Yeah. 'Cause
It can. So when we were doing those Carnot maps,
Mhm.
it did depend on how we defined them, because it could have been different if we had defined them differently, and so it can affect it. Okay, I am going to have to stop here, and yeah, I have to stop here. So
thank you so much.
you're welcome. Thank you for coming.